start here. Okay, so this one, as I said, this is as wound, so no set removal. Then how you read this one is, let's say if you're given a music wire, and you're using music wire, and you're finding this SSY, music wire as wound, then your SSY is 0.5 SUT. Okay. And your SUT should be find out from this table, from this formula, and A and M should be from this table 10-4, and D is the actual wire size, right? So then you can get your SSY. So this is how you can get the SSY. So unfortunately, this is not a fixed number, it's a range, right? So in our exercise or question, we will use mostly as a set before our as wound spring, just to be specific, right? Because this is a number here. Okay, so up to here, then we get our strings, right? So we're ready basically, let's see, to look at an example. Let's look at the spring design example. In this example, we're going to deal with is ideal spring. So ideal spring basically means you consider the compression of the spring is always proportional. So let's say as you have always done, when you calculate the spring, this is a proportional relationship, right? So force equal to spring stiffness times the deflection. So this is ideal spring. For a non-ideal spring, in the lecture notes, I have a dedicated section which I'll make it optional. So non-ideal spring basically means the first 15% and the last 15% of compression of spring are not considered as proportional. Okay, the proportional relationship between F and the deflection. So then how would you do that? So that's optional here. So we're going to consider ideal spring. Okay. In an example, okay, let's say I have a material called A22A music wire. Okay. And it's as wound spring, so no set removal. Given a spring wire diameter 0.006 inch, and also given the outside diameter 0.036 inch. Okay, so OD, this is outside diameter. The ending type of the spring, it's a square and grounded ending. Okay, so in this question, it specifically tells you the ending types of the spring, right? Now, I do need to be able to identify yourself that what type of ending the spring is. So this is the pictures in the lecture notes. Okay, so you can use to reference to different type of ending. We're talking about ground and square, which is this type at here. Okay. So if I give you a spring sketch like this, or any one of these at here in the exam question, okay, and without specifically telling you what is the ending type, then you need to be able to identify the ending type by looking at, right, the structures, the types of the ending at here. So then you can identify the ending, and then you can actually use this table 10-1 properly. Okay, yeah. So for simplicity, this one I told you earlier here, right? Okay. The total number of coil is 40 for this question. Okay. 40, again, the question gave you the total number of coil. And I think in the previous lecture I also emphasized the question may not give you the total number of coil. The question probably just give you a sketch of the spring like this. Then you need to count the total number of coil. Right? So 1, 2, 3, 4, 5, 6, 7, 8. So that's how you can get the total number of coil. All right. So just want to make sure these two here. Okay. So make sure you exercise a little bit. Just basically just grab any springs, okay, from your home or from a picture on the internet. Make sure you can count this NT. Okay, so you can count NT and also identify ending type. Okay, because these two are crucial initial information that you need to do the further calculation, right? So if you don't have these two numbers right, then literally you will get the whole question wrong. Okay, so now we can calculate free lengths. So LO, okay, not calculate free length. So the spring given a free length of 0.06 inch. And in this question, we're going to use a safety factor (1.2). So this is static analysis. Okay. For fatigue analysis, I do have a section, but I don't think I'm going to go there. We'll make it optional. Okay. Okay. So that's all of the given condition here. Now the question is it solid safe? Okay. Solid safe means if you completely press and close the spring, will the stress felt by the spring be smaller than the shear strength, and also by a margin of this safety factor 1.2. Okay, that's what it means by solid safe. Okay. Yeah. Okay, so this is the procedure to solve this kind of question. Okay, and there's a second part of the question, but let's solve this first, and then we'll look at the second part of the question. Okay. First step. Okay, this doesn't have to be the first step, but I'm gonna first find out the SUT. It's a musical wire we're using. So if I look at table 10-4, M is 1.145, and this is a inch series, so A is 201. And D is already given, it's 0.006, so you plug in everything. And this gives you approximately 422 psi. Okay, we've got SUT. So now let's calculate SSY, shear strength. So you use this table now, 10-6. This is 10-6. And we're talking musical wire as wound, so 0.45 SUT. And that gives you 189.9 KSI. Okay, now we get the strains, so let's calculate stress. So stress formula is KB 8FD over pi d cubed. KB again is 4C plus 2, 4C minus 3. And C is the spring index. It's the ratio between capital D and a small d. Okay, so capital D, small d, essentially, if you recall that, okay, maybe I'll just draw this picture here. So let's say if you have a spring, okay, so more precisely, your O in this question didn't give you capital D, right? What it gives you is the outside diameter. Capital D refer to the distance from the center to this center. And this is your capital D. Okay. So very simple geometric relationship. Your capital D equal to OD minus small d, which give you 0.03 inch. And you can calculate your C. You can calculate C now, and that gives you 0.03 over 0.006, which is 5. So now your KB, 4C plus 2 or 4C minus 3, end up so is 0.294. Okay. Okay, so we got our KB, okay, and we have our we don't have F yet, right? So F depends on the deflection. Okay. We do have a capital. So now let's look at how we get our F. So overall F, right, equal to the spring stiffness times the deflection. So we need to figure this F out. But we need this we need the spring stiffness first, and also we need the delta Y. Okay. So we're talking about solid safe, right? So basically you fully close the spring. Then you do have the free length, so the deflection will be the free length minus the length when they fully close. We call that solid length. Okay. So we need the solid length, LS. So LS, this is where you need to go back to your table 10-1 to look at LS, okay, depending on the types. When you have a square and a granite, your solid length is D times NT. NT is 40, so that gives you 0.24 inch. So now you have your deflection, okay, which is the free length minus the solid length, so 0.603, 0.63 minus 0.24, 0.39 inch. Good. So we got delta Y now. Now let's figure out the spring stiffness. Spring stiffness is that formula I showed you at the beginning of the lecture. Okay. And again, as I said, now you need to be careful. This is not NT, this is NA. This is the total number of active coil. So then what's the NA, right? So go back to the table 10-1 for square and granite. Here's the relation between total coil and NA. So NT equal to NA plus 2, so which means NA equal to NT minus 2. So it's 40 minus 2, 38. That's what you use for calculating capital K. And you already have small d and capital D. G is the shear modulus. So G at here, okay, I don't have the table at here. So G, you need to look at the table 10-5 in textbook. Look for the material given by the question, which is a music wire. So you'll find the G from the table 10-5 to be 12 mega psi for this D this much here. Okay, now once we find this, then we plug everything into this formula. We calculate this spring stiffness. And the results for this calculation and here give you 0.895 pound force per inch. Notice that I converted the psi to psi by multiplying 10 to the power 6. Okay, so the unit end up as just a standard pound force inch. So we are ready for the force, okay, or the load on the spring. So load is K times delta Y, okay, 0.74. So K times delta Y, okay, and 0.74 pound force. It seems to be a very small number, but you need to bear in mind this is a very small spring, right? The spring has a really small diameter. So now I can calculate my shear stress now. So plugging all of the numbers into the shear stress formula, we get 338.2 psi. Okay. Now this number is already actually more than SSY, right? So SSY you have find it, which is 189. So the shear stress is already more than SSY. So the safety factor here is already less than 1. But the actual safety factor required to be is 1.2. Okay. So which means this is not solid safe. Okay. So if it's not solid safe, right? So the second part of the question would be this now. What can we do to make it solid safe? Now, there are a number of things you can do actually to make it solid safe. This is basically the parts of design now. The first part you can call it analysis, and the second part you can think of as a design. So to make it solid safe, you could couple options. Number one option, you can maybe use a different wire diameter D. So maybe right, and the other one that will be actually in this case, this is what we're going to do. We'll use a different free length. Right, you think about it, the reason the tau is too big is because F is too big. So we need to just reduce F. Then maybe we can reduce the free length, right, to reduce the deflection. So then F will be smaller. Okay. So let's try this one here. Basically, what would be a appropriate free length to make a solid safe? sorry, LO. Solid length is LO. So here's how you can do it. Right? It's very actually simple. LO reverse, a little bit of reverse engineering. So LO equal to LS plus delta Y. So if we want to appropriate LO, then we need an appropriate delta Y. So LS you can change that, so that's solid length, right? Yeah. So we just have to find appropriate deflection or maximum deflection. Okay. So this is how you can do it. You have your SSY is already given, and then you have your safety factor. So you use this divided by that, then you get the total allowable shear stress, or the permissible shear stress, right? So that's SSY 189.9 divided by 1.2. Okay, so you can do the calculation and then do the calculation. Okay, so once you get this, and then this is a maximum allowable one. Your shear stress formula, right, is given by this formula, and F here is K times delta Y. So your maximum allowable, right, this value, okay, should be the maximum value for the shear stress, which is 8 times F instead of F. I'll replace that with K times, let's say instead of delta Y, it's called delta YS. So this will be the desired deflection, right? And the rest of the formula is the same. So we are just trying to figure out what's the maximum deflection at here, and that is constrained by the allowable shear stress. So you got all of the formula, you got all the parameter values here, right, except the delta YS. So you can calculate delta YS at here, and that turned out to be 0.182 inch. Right. So finally, your free length should be LS plus delta YS 0.422 inch. Essentially is your maximum free length. Okay, so that's an example for mechanical spring analysis and design. So in some other cases, you may be asked is what will be an appropriate wire size, right, in order to be solid safe. Okay, in this case, the design is the free length of the spring, okay, to make it solid safe. Okay. All right, any questions? Okay. So I think I'm going to stop here now. This is basically all exam required content up to this stage. The mechanical spring, I do have a few sections on fatigue loading. Okay, so you can take a look at, and also non-ideal spring. So you can take a look at the lecture notes for your own interest. Okay, all right. Okay, so I will make you the rest of the time to just do a very quick review. So I have this documented here, and I will upload it to Canvas, of course. But basically, just a summary, very bigger picture of summary of what we have learned, and after the midterm exam. Okay. The lecture numbers also listed here. Those are corresponding to the actual lecture number. You can use it as reference. After the midterm, we basically picked up on fatigue analysis. We looked at fatigue analysis under fluctuating loading and also combined loading. Right, so I should put a notes here. So fluctuating loading and also combined loading. This is just a theory part, right? So you can use this for many different applications. And then we started on learning different type of mechanical components, and we spent quite a bit of time on gear and gear design. So we looked at gear terminologies, spur gear, helical gear, and we also look at the gear design on spur gear and helical gear. So we focus mostly on the spur gear, but the helical gear is just slightly different from the spur gear. Okay. Now, if you recall, in this part of the lecture, we use ADMA equation, right? ADMA. And then shaft design, right, is not really new, but we have looked at the different considerations on the shaft, including the key design. And the bearing, so that's actually the part where things are starting to falling apart. Everything transitioned to online. So we looked at bearings, introduction to bearing and a bearing selection. There was 1 week, and I didn't really go online, but I posted videos from previous years. So you should take a look at this part of the video together with the lecture. They may not be exactly continuity may not be exactly smooth from the shaft to bearing, but it should be okay. We also look at the screw, power screw. Okay, so this part I think I went back to online teaching, but then had some trouble with the videos. We also looked at the threaded fasteners, how to get the stiffness of body joints, how to get the stiffness of member, and also how to analyze the safety of the joints. Welded joints, which happened in the last couple lectures. Okay, we looked mainly focused on fillet type of weld and also spring. Okay. Just again, just some of the major topics, right, for each part of the mechanical component. So when you review, make sure you look at this and ask yourself, okay, are you familiar or comfortable with the information behind this topic? Terminology. There are a lot of terminology for gear. Now, since the design project has been modified to only design for the gear, so by this time, and I would expect that you should be very comfortable or familiar with gear terminologies, including force analysis and also the design using AGMA equations. Okay. So in the final exam, look at one of the quiz. Right? I think quiz 3 is a type of a gear design question, okay, or analysis question. So some calculation will be simplified, but that will be the typical kind of question you would expect for gear. And maybe I will give you also maybe a sketch and let you to write down the terminologies or based on the sketch. For shaft, it's also a very important part of the question. However, because of this whole thing, and I have relaxed the requirement, not asking you to design for the shaft. But one of the quiz question basically illustrates the type of iterative process for shaft design. It's a simplified question, but the idea is very general. It's an iterative process. So you have a design equation for shaft diameter, and then you can iterate to get a minimum shaft diameter. Most type of a shaft design will be a combined loading, okay, and you choose a different type of design criteria. So there are quite a few different criteria, right? We use the modified Goodman quite a lot. But beside the design criteria, okay, for fatigue, there's one more step when you design shaft, is that you should also check the static yielding condition. Part of the shaft design is also designed for case. So case acting as a mechanical fuse. So when you design case, you should remember case should fill first, right? There are two different formulas designed for key. We focus mostly on rectangular or square case, right? So you design For square case doesn't matter. For rectangular, you have this compressive bearing stress and also the surface compressive stress, shear stress. Yeah. Power school. Okay. We look at the terminology. We also look at the mechanics of power school. In this part, there's a formula derived to calculate how much torque you need to raise or lower the load. Okay. There's a condition called self-locking. So if the friction is very low, then the nut could actually drop by itself. We also looked at the different stress at different locations. Now, as I said in this part of the question, I do not need you to remember all of the formulas for different stress, but I do need you to be able to identify the type of stress at different locations. So take a look at the lecture notes. I believe it will be this one here. And the lecture notes essentially lists of different type of stress, and these are good examples. If I ask you what type of stress exists at this location, so those are the different stress, right? Similarly, what type of stress exists at this location. So you just need to identify what's this stress, what this stress, and what this stress, and where their origin is. So you don't have to remember all these formulas, but then again, you have to open book, so it won't be a problem. Threaded fastener. Okay, this part here, and I feel this is the part, the question that requires you back and forth looking up tables in order to solve a question. First of all, terminology, okay, and then when it comes to the fastener stiffness or ball stiffness or member stiffness, okay, so you have quite a few tables you can make use of in order to find a solution. So this is where I would encourage you to look at the tables. I have uploaded this. I have basically collected all the necessary tables, okay, in this file. So you can actually save you some time to look into your appendix or actual topics, actual tables in textbook. Okay. It may not have every table, but I think it should have all the tables. Okay. Yeah. So 29 and 30. Okay. So take a look at that. You can print it out and use it when you're answering the final exam questions. Okay. It'll come handy. Ball strengths, okay, that you also need that number in order to analyze the safety of the tension joint. And this is where we look at the tension joint. Now I think I covered both static and the fatigue, but we'll focus on the fatigue loading only. A welding joint, okay, first is the welding symbols. So I showed you a few different welding symbols. But fillet weld is our focus. Okay, the requirement is when you look at the welding symbol, you need to be able to identify what type of weld it is and what's the leg height, right? Where is it going to be weld? Is it all around, or is it on one side, or is it on both sides? Right, so that type of information. Okay, stress. Okay, there are two different cases. One is in plane, the other is out of plane. So in plane means the force and weld group are in the same plane, and out of plane means the force and the weld group, they are actually not in the same plane, called it out of plane. These two cases correspond to two different tables, 9-1, 9-2, to give you the polar moment area and also the second moment area. One is J, the other is I. So I emphasize the importance of this step here. When you analyze welded joints, you have to be able to properly identify this in plane or out of plane. If you this step is wrong, then all of the analysis following this will be wrong, right? Now strengths, depending on what you analyze, but in this textbook, in this class, I emphasize that we will consider welded joints as doesn't matter where we consider it's a combination of a base material and the electrode or filler material. So we do need to apply the welding code, but before we apply welding code, we had to find out the material property for both of the base material and the electrode. Static loading only for welded joints. Okay. Spring is what we have just finished. We focus on the mechanical compression spring. Spring is a shear stress in it, and you have also again you have different tables. Okay, to look up to, before you can find the right value. So that's all we have learned after the midterm. So before the midterm, you have the static analysis, right? You have free body diagram for typical shaft loading. Now we're not going to have a midterm questions like questions testing the failure theories, but you do, as you can see in each part of the component, you do use the static and the fatigue loading theories, right? Analysis theories. Okay. For shaft design, inevitably you still need to be able to draw a free body diagram, calculate the bending moment at point of interest, and then calculate the normal stress, right, based on the bending moment. Okay. But of course, in this case, we're dealing with the combined loading and also fluctuating loading, right? So when you have a shaft design question, it is inevitable that you still have to be able to do all of these things. Okay, so the final exam will not be cumulative, but it will be comprehensive. So I won't have a question dedicated to materials before the midterm, but in most of the cases, you do still need to understand and able to carry out the calculations using the knowledge that you learned before the midterm. So that's the requirement for the final exam. Okay. Okay, so we will have questions for those major topics added here. Okay, and the format of the final exam will be similar to the midterm. So there will be maybe a few multiple choice and then plus a few comprehensive short answer questions. Okay. The number of questions, as I explained, okay, and although you will have 24 hours, but exam will be designed for 3 hours exam. So in most of the cases, when I design for 3-hour exam, we actually design so the student can finish. Majority can finish maybe with 2.5 hours to 3 hours. So depending on your pace, right? Some student maybe even can finish early. Okay. So that's the expectation for the final exam. So now because it's 24 hours, then it's all open. Okay, so because again, I don't have control over what you're going to use, so might as well just all open. It used to be just open book, so now you can open book and also open lecture notes, right? Okay, a calculator, so you can use any engineering calculator. Now you have a calculator computer, so you can actually use, if you want to use a MATLAB to calculate, that's fine. But you do have remember, right? I mean, even 24 hours, but I don't want you to work on it for 24 hours. Okay. After you finish, okay, please make sure you scan it and upload back to Canvas. Okay. So I will put it under assignment. I haven't created yet, but I will put it under assignments. Okay. Another thing, before you start your final exam, which will be released on April 23rd at 9 p.m. I want you to finish this integrity pledge question. So last time I checked, not everybody done it yet. It's very simple. It won't take you more than 10 seconds to finish this. However, I do need you to answer this question. There's only one answer. Unfortunately, it's not a multiple choice. Only one answer. You just have to agree to this integrity pledge. Excuse me. If you don't do this, and I will reserve my right whether to grade your final exam or not. This is the honor system, right? You agree on it, and then I will trust you that you will adhere to the pledge, adhere to exam requirements, okay, and you will not collaborate with other students or other people. Okay. It's honor system. Again, I said it is an honor system. Even you do that, but nobody will find it out. But again, this is right self-honored system. Okay, so please do answer the question before you start your final exam. Okay. What else? Project due date will be next. Can't remember. Is the next? Did I say next Monday as a project due date? I can be a little flexible if I can remember what I said now. Yeah. Okay. So I can be flexible. If I said it earlier, other than next Monday, then that's fine. Okay. So just make sure that you submit your projects before next Monday. The summation is also through the Canvas, right? You um, you should also submit the Excel file. Yeah. Okay, I got a question. Is cover? I think I explained that, right? So submit both of your PDF file plus the Excel file. So I'll look at your Excel calculations. I'll see if you have any mistakes when you do the calculation. Okay. Okay. So what else is there? The exam is still a little bit, a few weeks from now, so you have quite a lot of time. But I understand you have many other exams, of course, right? So I think I emphasized, it's only about 2.5 weeks, maybe 3 weeks. So make sure you're healthy. Make sure you can pull through this exam period, right? So it's going to be a very tough period here, right? And stay healthy, stay nourished, and you can focus on the exam, right? So I think everybody is trying to accommodate different situations. Um, Different people have different accommodations, right? So make sure you understand the type of exam from different courses, and also the formality of the exam, right? Don't violate any exam rules. Any question for me? I won't disappear, and I will make myself available. Please actually send me an email, and I find when I make an office hour, I don't know if nobody's actually comes, so just shoot me an email if you have a question. We can work on a video if I can't answer this easily, and we can always set up an online meeting individually, right? So, but otherwise, if I can answer through email, then I can through email, right? Okay. Any question for me? No, no question. All right. So if there's no question, really appreciate everybody for this difficult term. It's not ideal, but I think we we got our points done. You know, we have accomplished what we wanted. It just you know, it's not going to be happy for everyone, right? But it will go back to normal, I think. Okay. All right. So I will communicate with you through email or Canvas. Okay, and also don't hesitate to contact me through email. Okay, everybody. So good luck with your exam. And thank you, everybody, too. I know you have been a hardcore student. Um, the attendance is not great, but I really appreciate that everybody here, the names are all familiar. Um, Sticking to the online lectures as much as you have coming to real person in-class lectures. Okay. We'll see you in 2000 September 2020.